All right, well, it's noon, so we'll get started here. So welcome to CS50 week 3. This week we're going to be talking about algorithms, recursion, structs, and let's dive in. So I'm Kelly, as if you've seen me in last week's section or in lectures, I'm the preceptor here at Harvard. Here's my email if you ever feel like you need to contact me. And excited to be running this section. So today we're going to be talking a little bit about some of the things we saw in lecture this week. First, what are structs? What are these things that we can create? How does recursion work? And that's the basis of one of the searching or sorting techniques we saw, merge sort. So how can we search and sort efficiently? And how can we measure that efficiency? So what is big O notation? So you heard about these things in lecture. Today we're going to go a little bit more in depth and review them in a more hands-on way. So first we're going to start with structs. Basically, we're coming at this with the question of how can we group different types of related data into a single unit? So I have different kinds of data, and it would be nice to have them grouped in a unit that I can use over and over again. So an example of this might be if we're tracking the candidates in an election per se. And so this is an example of what a struct could look like. It starts with the keywords typedef struct, and it's called candidate. In this candidate struct, we have two pieces of data that we're storing. So the first being a string called name, and then the second being an integer storing the number of votes. So typedef here is just saying, like, we're going to create a new definition here, or a new type, and candidate is the name of this new type. Within those curly braces, we have grouping the new kinds of data that we want included. So this could be many, more than two, less than two, it could be one, but it's likely going to be helpful if you're trying to group many pieces of data together. So if we want to create an instance of this type, so we've created the type, say like an integer, now it's called a candidate. And then we want to create one candidate, and we're going to call it, say, president. If I want to give president the attributes that I showed here, the notation looks a little bit like this. So just like before, we have president, which is the name of the variable, and then we're getting the name, so .name, and setting that to Alice in this case. And then the same way, we're doing .votes and setting that equal to 10. Okay, so I'll pause here for any questions so far about structs. Feel free to drop them in the chat if so. If not, I'll move on. Feel free to continue to put things in the chat if they come up. So we're going to first start out with a little exercise, trying out the things that we just saw here. So we're going to try to create a struct that represents a candidate in an election that includes the candidate's name, the number of votes as an integer, and we're going to add those attributes to a candidate and print that out to the user. So if you're watching this asynchronously, feel free to pause here and try this out for yourself. But we're going to go ahead and move to VS Code and try it out. Okay, and would love to have participation in the chat, so feel free to write your thoughts, and I'm going to be asking you a lot of questions. So we're first going to start out by creating a struct.c file, and first thing we're going to do is import some libraries. So we drop in the chat what libraries might I need to import here. Standard IO, yeah, great. Standard IO.h. Someone says string.h, CS50x. Okay, great. So I'm going to start out with including maybe just these two for now, and we'll see if we need string.h later. And then we start out with int main void. Okay. So I know I'm going to need to create a struct. And so does anyone remember where in my code that goes? My like type def struct. Perhaps which line of code should that be on? Before main. Yeah, exactly. So we want to define this before main. So we're going to start out with type def struct like we saw earlier. And this is going to be called candidate. Within this, we're going to have two pieces of information like we saw earlier. A string called name, and then an integer called votes. Okay, great. So now we have that. We want to add these attributes to a candidate. So say Alice with 5 votes. So how would I go about creating an instance of this candidate? So I know I want it to be of candidate type. Then maybe I give it a name. So I'm just going to say A for now. Okay, and now I'm going to give it its attributes. So I called this candidate A. And then how do I go about adding the name? What do I type after this dot? Someone says president. Okay, yes, dot name, exactly. So dot name is Alice. And I'm going to set a.votes in the same way to 5. Now I can go ahead and print this out. So I'm going to do %s for Alice has %i number of votes. Okay. And then what do I put in here for my placeholders? If I want to substitute, Alice has 5 votes. Okay, I'll do a.name and then a.votes. So a.name will give us Alice, a.votes will give us 5. So that will substitute. Okay, so let's try making this. Oops, okay, make struct. Okay, /struct, and then we get Alice has 5 votes. Okay. Any questions about this code so far? Okay, well, feel free to drop in the chat if you do. For this next part of this exercise, we're going to make this a little bit more interactive, and we're going to create your own getCandidate function that prompts the user to input attributes for a candidate. You may rely on getString, getFloat, etc., and your function should return a candidate. So in my current function, I'm setting these values myself. That's maybe not as fun as getting that information from the user. So we're going to create a getCandidate function. So I'm going to set that up here. So, well, first I should ask, what is this getCandidate function returning? So what's the return type of this function? So I know that I want to take in, someone says string, not quite, right? We want to return a candidate with those attributes. So something like A here, candidate, exactly, yeah. So we're going to be returning something of candidate type. Call this function get candidate. We're not going to take any inputs since we're going to be prompting the user. Okay. So first, I'm going to ask for the attributes, right? So we're going to do like new, or yeah, we can say the name is going to be, we're going to get that from the user, so name. And then we're going to ask for votes, int votes. All right. And then how am I going to declare a candidate down here? It's going to be similar to what I did up here when I hard-coded these values in, right? So maybe I'll make a new candidate variable, call it new candidate. And now that I have these values from the user, I can set .name to name, and I can set new candidate .votes to votes. Okay, I'm going to pause here. Does anyone see anything that I could potentially improve on with this code? Are there any variables that are not necessary? How could I improve the design? Feel free to write in the chat if you have an idea. Someone says add comments. That's a good idea. Actually, we should add some comments. So maybe I'll say, this is a function to get a new candidate. So this name and votes variable are not necessarily needed here. Like I could just take this and move it here, right? So I was just using that name variable to store it temporarily. But that's precious memory that we don't necessarily need to be spending, since I can just store it right in the new candidate here. So already we've shortened our code a little bit, which is nice. Okay, and someone also mentioned the return. Yeah, so once I've actually created my new candidate and given it the name and the votes, then I can return new candidate. Okay, so that's our function. Now let's go back to our main function and actually use it. Okay, so we're gonna say maybe we're gonna create a candidate. Perhaps I also call it new candidate. And then I'm gonna store it, or the value that I want for this new candidate is gonna be coming from this function. So I'm gonna do get candidate like so. All right, so basically I've created a new variable called new candidate of candidate type, and it's gonna be equal to the return value of this function. So it's going to run this function, going to ask for a name, of votes, and then return to me a candidate with that information. So once I have that, then just like before, I might want to print that information. So I could say candidate is named and then a name, and has some number of votes. Okay. I'm going to substitute here just like we did before, new candidates dot name, and then for the votes, new candidates dot votes. Okay, so let's make again. Okay, what happened here? So we have error, call to undeclared function get candidate. Does anyone know what is going on here? Why am I getting this error? Someone said no prototype. Yes, exactly. Yeah, so if we recall, a prototype or prototyping a function means to take this function and the first, this first line of it and make sure that we declare it before the main function. So otherwise, we get to the main function and the compiler gets to this line and it's like, I don't know what this function is. I haven't seen this before. So by prototyping it here, we can be sure that the compiler knows, okay, there's going to be a function that's named this. Okay, so I'm going to clear and make again. Okay, what happened here? Oh, I just had a typo. Okay, new candidate, so that should match with this. Okay, so I have ./struct, I'm gonna run it. I'm gonna give it a name, Alice. Maybe she has 10 votes, and we see candidate is named Alice and has 10 votes. Perfect. Okay, so I'll pause here again, see if anyone has any questions about the code we just created. Okay, someone said they're still having trouble with calling functions. Yeah, so I'll try to go over that a little bit here. So in this main function, we're creating a new variable and we're setting it equal to the return of this function that we've created, getCandidate, right? And so this function that we've created separately, we know calls getString and getInt to get that input, and then it returns a variable of candidate type called newCandidate, right? And so that candidate that's being generated in this function then gets stored as newCandidate here. So hopefully that helps. And feel free to write more questions in the chat if you have them. But we're going to continue. Okay, so that was if we just had one candidate that we were storing and we were returning. But what if we have multiple candidates, as you usually do in an election? What might I use? Yeah, someone says we might need to use arrays. So we could imagine we have an array like this called candidates, plural, of type candidate. And we're going to store 3 candidates inside of this array. So with each candidate, we know we are also storing a name and number of votes. And so if we have the first, the first candidate here, it's going to be referred to as candidates at index 0, right? So we're going back to our array indexing, and the first is always going to be at index 0. If I wanted to give it a name, then I do a similar notation here with the dot name and set that equal to Alice. Same thing with votes. I can do candidates at index 0, dot votes, set that equal to 2. Okay, so you can do that same thing for candidates at bracket 1, at bracket 2, and fill those values in the same way. Okay, so we're gonna see this in practice, but any questions about that? Okay, let's try this out here. So we're gonna see, someone says, is it possible to store arrays inside of arrays? Yes, so we have like two-dimensional arrays. So you can have arrays of arrays. Good question. And you're gonna see that in a few weeks. Okay, so we're gonna keep building on our original program and use our getCandidate function to create an array of 3 candidates, each of which should have attributes input by the user. Okay, so we're gonna come back here. So right now we're calling this once to store 1 new candidate, but now we know we want 3. So, like before, we were using arrays. So I'm gonna make a new array, candidate, and I'm gonna call it candidates, plural. And I know I'm gonna be storing 3, so I'm gonna set the size of that to 3. Okay, so now if I wanna go over each candidate and fill that with the information from the user, yeah, someone already beat me to the punch. So making a loop, we should make a loop here to do that 3 times. So I'm gonna repeat from I equals 0 to I less than 3, so that it repeats 3 times. And then within that loop, I want to get a new candidate. So I'm gonna do candidates. I wanna go into the array at index of what here? If I wanna first do so we wanna do the first, the 0th, the 1st, and then the 2nd. So I'm gonna use I here, do candidates I, and then I'm just gonna call getCandidate. So that way we're calling this function 3 times, and each time it's going to create, or it's gonna fill up this index in our array so that we have 3 candidates. Okay, great. Okay, so now that I have 3 candidates in my array, how do I go about printing them? So I could print out just like candidate 0, candidate 1. Yeah, people are saying a loop. Yeah, we're gonna do another loop here. And it's also gonna repeat 3 times. Okay, and then I'm gonna have a print function just similar to this. And so we're gonna say candidate is named the name and then has some number of votes. And then what am I gonna be putting here for the name? If I want the first candidate's name, candidate at index 0. So I have candidates, at index I, exactly, and dot name. Okay, cool. And then we can do the same thing for votes, so candidates at index I dot votes. Okay. And maybe, honestly, it might be nice to know which candidate I'm on. So I could say like candidate 0 or candidate 1 is on, has this name and has this vote. So maybe I could say candidate I here, and then print out I, so that I have, someone's saying maybe it's kind of weird to do candidate 0, so I could do I plus 1, so that it starts with candidate 1 is named blank, candidate 2 is named blank, candidate 3, etc. Okay, great. So let's try this. Oops. Let's try this out here. Bring my terminal back. Okay, so I'm going to make struct. Nice, no errors. That's good. Okay, so we have first name, say Alice has 5 votes. Second one's named Bob, has 9 votes. And then we could say Charlie has 2 votes. Okay, so we have candidate 1 is named Alice, has 5 votes. Candidate 2 is named Bob. Candidate 3 has 2 votes. Okay. So any questions about this code? Someone says, can we combine these 2 loops? Yeah, that's great instinct, right? We're kind of seeing this repetition here. What if I just moved this here? Okay, so how does this change the way that our program runs? It does make it a little bit different, right? So yeah, someone says it can become jumbled. What does that mean? So when I first ran it this time, I inputted these 3 things first, and then it printed out the 3 candidates. But if I make this again, and I do struct, I do Alice has 5 votes, it's going to print that out to me immediately now. So I can say Bob has 10 votes, Charlie has 2 votes. So the function does act a little bit differently than it did before. So really, in this case, it is up to the programmer to decide what is the intended function of these of your program. Okay. Someone says, don't the values print themselves? Why do we need to print them? So anytime you want something to print to the terminal, you have to use the printf function. Yeah. Otherwise, these values are just stored in our variables, but they're not necessarily going to be printed out. Hopefully that answers your question. Okay, so feel free to write any questions if you have any about this function, but we're going to move on. So next we're going to talk a little bit about, but doesn't getString print too? Yeah, it does. Yeah, so part of the getString and getInt function, the way that it's programmed is that if you pass in a certain string here, it's going to print that before inputting this here. Someone says, couldn't we put the printf outside of the loop? So you could put it out here, but then you wouldn't be able to use the index I here since it's not in a loop, right? And so if we were to use it outside of a loop, we'd have to have this 3 times for each of our candidates, which isn't the most efficient here. Okay, so we're going to move on to recursion. And recursion is the basis of one of our sort algorithms, but it's also just a general technique for solving problems. Someone else said in the chat, can a for loop inside of another for loop do the same work as you did before? Okay, so when you have a for loop inside of another for loop, that's going to loop more times than, so like if I had another for loop that loops 3 times within this, it's going to print out like 9 times, right? And so what we had before here was just another for loop of 3, like so. Yeah, and so we would like to have 2 separate for loops that are at the same indent, right? So that we're not repeating ourselves more than we need to. Okay, so hopefully that answers your question here, but we're gonna move on to recursion. So what is recursion? Basically, it's solving a problem by first solving a smaller version of that same problem. So a recursive function is going to have a base case that tells us when are we going to stop running this function, and then it's also going to have a recursive case, which includes a call to the function itself to solve a smaller version of that. So it's kind of a thing you have to wrap your head around, and it's not immediately obvious. So let's go through an example, and hopefully that makes this idea a little bit more clear. So we have an example here of factorial. So if you've heard of factorials before, basically, for example, the factorial of 5 is 5 times 4 times 3 times 2 times 1. Factorial of 0 is also 1. And so basically, the factorial of any number is going to be that number multiplied by every other number less than it until 1 or 0. Okay, and so we're going to think about how we could create a function called factorial that takes an integer n and then prints out the factorial of n. So let's walk through some of the logic behind this first before we dive into the code. So let's say we're looking for the factorial of 3. So we can write that out as 1 times 2 times 3, right? The factorial of 2 is 1 times 2. Factorial of 1 is 1. Factorial of 0 is also 1. So if you're kind of seeing a pattern here, you could also write this as 3 times the factorial of 2 equals the factorial of 3. 2 factorial is equal to 2 times the factorial of 1, and etc. Right? And so if we're thinking about this in a recursive way, we have the call, maybe f is our factorial call. So calling f of 3 is going to give us 3 multiplied by the factorial of 2. And then we want 2 to be equal to 2 times the factorial of 1. 1 is going to be equal to 1 times the factorial of 0, and factorial of 0 is 1. So when we're actually computing this, we kind of go down this loop, or not loop, we go down recursively each call, and then we can start computing those values back up, right? So we have factorial of 0 computes to 1, and then 1 times 1 is 1, so factorial of 1 is 1. And then 2 times 1 is 2, so factorial of 2 computes to 2. 3 times 2 is 6, and then we have finally factorial of 3 computes to 6. Yeah, so we're calling this function recursively until we reach back up to the top with our final value. Okay. So in this scenario, what is our base case? What's the case where we should stop calling recursively? Yeah, someone says factorial of 0, exactly. So we know factorial of 0 is 1, and we can say that is the stop. You could also do 1, yeah, because we know that factorial of 1 is also equal to 1. And then what's the recursive case? So if we're not at 0, what should we be doing? Yeah, someone's saying like going to the factorial of the previous number. Yeah, exactly. So it's going to be calling the factorial function again, but now with the number below. So n minus 1, I guess. Okay, so let's actually try to see what this looks like in code. So I'm going to make a new program called factorial.c. Okay. We're going to copy over our header files here. Do int main void. Okay, cool. And so we know that we want to first prompt the user for some number that we can then get the factorial of. So I'm just going to say int n get int, and we're gonna say factorial of what number, and the user can input it there. Okay, and now we want to set up a factorial function. So just like before, what is going to be the return type of this function? Int. Yeah, exactly. So it's going to return an integer. What is the input type? What should it take in? Not quite void, since we want to be doing something. Yeah, int. So we also want to be taking in an integer, and we're going to call it n, just for the sake. Okay, and so I know we want to have our base case, and we also are going to have our recursive case. Okay, so in the base case, we're going to check what we said before. If n is 0, then what should I return? 1, exactly. Return 1. That's what 0 factorial is. Okay, so if I haven't reached 0 yet, if n is not 0, then I should be returning what here? I know it's going to be recursive, so it's going to call factorial again with the previous number. Yeah, exactly. So n minus 1. And it's going to be the factorial of like 5 per se is going to be 5, which is n, times the factorial of the number right below it, which would be like say 4, right? Okay, so once I have that set up, I'm also going to make sure that I prototype it up here, and then we can print out the factorial of n. So you could say factorial of %i is %i. So we're going to have two integers here. The first one being n, which is just the number that was inputted to me. And then the factorial of blank is, I'm going to call factorial on n. And that's going to be the result here. Okay. So I'm going to make this factorial. Okay, so let's test it out. Factorial of 0 should be 1. Oh, I forgot a new line here. Okay, so I'm going to add that. Recompile. Okay, factorial of 0 should be 1. Great. Factorial of 1 should also be 1. And then let's say maybe factorial of 5 is 120. Okay, so it looks like it works. Feel free to write in the chat if you have any questions about this. Someone says, how does this work? Can't we just use a loop instead? Yeah, exactly. So anytime we have a recursive function, you can also do it iteratively. Like those are two different ways of solving the same problem. And by iteratively, I just mean by using a loop, doing it one by one, right? So we could totally write a version of this that uses a loop instead of doing this recursion here. But just to like break down how this is working, I can say in this 5 example, we have first asking, you know, what number do you want? And then I said 5 in this case. So n now is equal to 5, right? And then I print out factorial of 5 is factorial n. So it's calling this function where n is 5. And so we run through, it's not equal to 0, so then I say that, okay, I'm actually going to be returning 5 times factorial of 4. So this calls again, and then we go through this again and say, okay, actually factorial of 4 is 4 times factorial of 3. So then we are at this function again. It's not 0, so I go to this recursive case, say 3 is factorial of 3 is actually 3 times factorial of 2, so on until we get n equals 0, right? So we're calling, if n is 0, then we return 1, okay? And so then we're computing those values back up the chain, just like we had in this diagram here, right? So this f here is our factorial function, and it's returning 1, and then it's returning, then we get this value computed, right? And so that computes to 1, and it computes up to the first thing that we asked for, which was, in our case, factorial 5. So hopefully that makes a little bit of sense. How can you call the function in the definition of the function itself? Yeah, that is the definition of like a recursive function, yeah. So in recursive functions, we're allowed to call the function itself. The reason why it doesn't go on forever is because we have this base case, right? And so if we didn't have this, then indeed my program would just go on forever and forever, going to like n equals -1, -2, -3, into infinity. But because we have this base case that does actually return something at some point, that is the reason we're able to have this recursive function actually end at some point. Okay. The function is defined, yeah, on line 12, as someone said here. Yeah, okay. So that's recursive functions. We're going to show another example of this and work through it here. So again, if you're watching this asynchronously, feel free to pause and try this out for yourself. But we're going to do this live together. So we're going to write a recursive function fib that takes an integer n and then prints out the nth Fibonacci number. So if you're unfamiliar, the Fibonacci sequence is a sequence in which each element is the sum of the two elements that precede it. So this is an example of Fibonacci sequence. So we can see it starts with 0 and 1, and then the next one is 0 plus 1, which is 1. The next one is 1 plus 1, which is 2. The next element is 1 plus 2, which is 3, etc. So let's try this out pretty quickly here. So I'm going to code fib.c. Okay, I'm going to copy these over. Oops, int main void. Okay, so I'm going to do a similar thing where I ask for some integer. Say like, which Fibonacci number do you want? Okay, and then I'm going to print something eventually. We'll get to that. Okay, my Fibonacci function here is also going to take in a number, except also, I guess how many inputs should it be taking is the question. How many pieces of information did I need to know to calculate that 2 is the next one? Yeah, so I need 2 pieces. I need like the element before it and also the element that was before that. Okay. And so that gives us a hint to what our recursive case is going to be. But let's maybe just say that this function, it takes in like the number of the Fibonacci sequence that you want. So like takes which Fibonacci number you want and then returns that. Okay. So again, we're going to have a base case, and we're going to have a recursive case. And so like we said just a second ago, I know that I'm going to need like the Fibonacci number that was right before it, and also the Fibonacci number that was before that. Okay? So this is like this recursive case. We're saying that the Fibonacci number of n is going to be the Fibonacci number of n minus 1 plus Fibonacci number of n minus 2. Then what is our base case going to be? When should this recursive case not run? Yeah, so someone says 0. So if n equals 0, then I should return, what is the Fibonacci number of, or the 0th Fibonacci number? I don't know if that, yeah. Okay, return should be 0. Okay. What about this n minus 2 case, right? So like if I ran int of 1, then this would return fib of 0, which I have defined as 0, plus Fibonacci of negative 1, which doesn't seem quite right here. Yeah, so someone's saying, what if n minus 2 doesn't exist? So we've defined n is 0. So what I might need to do here is actually also define n equals 1. Say, what is the 1th Fibonacci number? Yeah, 1. So if we're saying this sequence is 0 indexed, right? So the 0th is 0, the 1th is 1. Then the next one, 2, the second, is in n0, like Fibonacci of 0 plus Fibonacci of 1. Okay. So now this is going to cover the case that I just described, right? If I call Fibonacci of 1, it's not going to go to this case and try to return Fibonacci of negative 1, because that just, we have not defined that as existing. Okay, so now I can go back here and print out, say, the ith Fibonacci number is I. New line, I'm going to say that return n here, and then return fib of n. I'm also going to prototype this so I don't forget here. Okay, so that's our code. Don't forget a semicolon. I'm going to make this /fib, and then we see, okay, I want the 0th, that should be 0. Cool. Next one should be 1. The second should be also 1. Nice. Oh yeah, I guess this th is not always going to work for like second. Okay. And then let's say like the 5th one, 5th Fibonacci is 5. Is that true? 0, 1, 2, 3, 4, 5. Yeah, that looks right. Okay, cool. So feel free to write any questions in the chat about this program, but this is just another example of how recursive functions can work and how we can call the function itself inside of the function. Okay, so we're gonna move on to searching and sorting. So I'm going to first pose this question. If you had like this array of integers, but you don't know what's in each one, how would you go about searching for 6? If I told you you should look for 6, what's your approach or your algorithm per se? Someone says sort first. Okay, what if I can't sort it? Someone says search linearly. Yeah, so like maybe I just go through them one by one from like left to right or right to left and check, is this 6? So I could say, I'm gonna open the first one, it's not 6. Next one is also not 6. Keep going, this is not 6 yet. Okay, and then I found 6. Okay. So we're gonna talk a little bit about this fancy word called runtime analysis, but really this just means how long did it take to do what I just did, this algorithm that I implemented that was called linear search. How many checks are needed to search for 6 here? So I think when I just did it, it took 4 checks about, but someone's saying n. Yeah, so like the length of this list. I don't know which one it could be, so it could be 8 checks. Okay, what about this list? Yeah, and again, it's going to take however many inputs I have in this array to check. So I'm going to have to check every single one, which is not super efficient. But we call this a big O of n. And basically this is saying that I need to do as many as n steps for an input of size n. So however long my input is, I need to do that many steps. You can also think of this as the way that the algorithm's time that it takes grows over time. So it scales linearly with the size of our input. Right? So for each new item that's added to my algorithm's input, the algorithm needs to do a fixed number of new steps. Yeah, and it looks a little bit like this linear graph, as someone said, because if I say double my input, I make it double the size of the list, then it's also going to take like double the size or double the amount of time to search that list. Okay, any initial questions about searching? Okay, if there are, you can put them in the chat. And we're gonna move on to sorting. So some people said like, oh, you should just sort the list first before searching it. And how are we gonna do that? We have 3 different sorting algorithms that we're gonna go over. And first we're gonna talk about selection sort. Okay, so we have a little animation here to show you what selection sort's looking for. Okay, we have a few questions. How do you figure out what approach to use in searching? Yeah, so the only one that we've really talked about here is linear search, but it always depends on the context that you're using this in, right? So you could also just open up doors randomly per se, like we just check random indexes until we find the one we're looking for. But depending on how often you're going to need to be doing this searching and what the data is that you're searching among, that might help you choose a certain approach over another. But yeah, that's a great question. Someone says, what about the average runtime instead of an upper and lower bound? Yeah, so I think you're referring to theta, which was brought up yesterday in lecture. And so that is used when the upper and lower bound are the same. So like in the upper bound case and the lower bound case, both of those runtimes will be the same. But yeah, usually this big O and big omega that we'll see are typically used to describe, to give you an idea of like how much time it's going to take in upper bound and in lower bound terms. Okay, so let's look at selection sort. So I have this list here. It's unsorted, as we can see. And the approach we're going to take with selection sort is we're going to look for the minimum value in this list, and we're going to store it in this minimum variable. So I'm going to go through, I'm going to check. Okay, 5. Okay, 3 is my current minimum. Let's look for something lower than 3. Okay, 2 is lower than that, so I'm going to update it. And 1 is lower than that. Okay, great. So because I now have this minimum, I know that that's going to go at the beginning. So I'm going to swap 1 and 5, which is great. And then we're going to do that again for as many integers we have in this list. So I know that the first one's sorted. Now I can focus on the second value in the list. So 3 is my current minimum. I'm going to look for something lower than that, which is 2. And then there's nothing left lower than 2, so I'm going to switch 2 and 3. Okay, we're going to start at 4. 4 is my minimum. Look for something lower than that. It's 3. And there's nothing else to lower than that, so I'm going to switch it. And we're going to do that process again, switching and finding the minimum until we have a sorted list, like so. Okay, so what was that process that we just did here in sort of pseudocode? So for every element in our list except for the last one, so we didn't do it at the end because we knew that that was going to be sorted. Or I should say, if we're doing 0 indexing, then we're not going to include the nth element. Assume the element at this position is the smallest, right? So I started at the first element and just assumed, okay, that's the smallest one I've seen. And then for every element to the right of that, if it's less than our current smallest, we're going to update the current smallest. And then once we get to the end, we're going to swap the current element we're on with the current smallest. Okay. If we use some of our indexing language here, we can rewrite this sort of like so. So we have for I from 0 to n-1, or n-2, right? So we're not going to do that step for the last element in the list. So we can see that once I was here, we already know that 8 was going to be sorted, right? And so we're going to set some minimum value to I, which is that first element, or the current element. And then we're going to loop from I plus 1, which is the next one, to n-1, which is the end of the array. And if that value is lower than our minimum, we're going to update that. Once we get to the end, we're going to then swap the ith element with our minimum element. Okay. So what does the runtime look like for this? We have n squared. Someone want to explain maybe why is this n squared? Why am I going to need to do as many as n squared steps if my input size is n? Well, you can kind of see when I was showing you this example. Yeah. So I had 8 elements in this list, right? And so in this first pass here, when I was looking for the first minimum, I looped over every single element in this list, right? So n number of times to find that 1 was the minimum, right? And then I do this sort of thing again. I guess now I'm not looking through n number of elements, but I'm still n-1, right? So it's still on the order of n. And so I do that searching n number of times because I need to sort every element of this list. Okay, so eventually we get to n squared as our upper bound because it could take, we need to see each element within each pass and then n number of passes. Okay, our omega, which is lower bound, is also n squared. Right, so in the best case, I'm still going to approximately do n squared steps. And the reason for that is because if in my best case, which is like if the list is already sorted for me, I'm still going to do all of these steps. I have no way of like checking early that this list is actually sorted, and I don't need to be doing all this work. Okay, we're going to move on now to bubble sort, which is slightly similar in some ways, but different in others. So basically with bubble sort, we go through the list checking 2 by 2. Are these out of order? We're going to ask that question over and over again. If they are, then we're going to swap them, right? So then I'm going to look at 5 and 4. These are out of order, so I'm going to swap them. And so on until I get to the end of the list. And now we can see that the largest value, in this case 8, has bubbled its way to the top, or to the end of the list. So we now know that 8 is in the right spot. So basically now we just repeat that process for the rest of the list, right? So we're going to go through, this first pass is now complete. We know that 8's in the right place. Okay, then we go through 2 by 2. We see that 2 and 5 are out of place, so we swap them. And then 7 and 6, or 1 and 5, yeah. Then 7 and 6. And that's our second pass. Now we know 7's in the right place. Okay, and then we know that 6 is also in the right place. I don't have to, but I'm gonna make this swap between 2 and, so we have 3 and 4 in the right place, 2 and 4, we're gonna have to switch. 4 and 1 we switch. The rest are good. So I know for sure that 6 is up in the right place. So on and so forth. We're going to keep making those swaps until we have a fully sorted list. Okay, so our pseudocode for this looks a bit like this. For every element in our list, except the last one, we're going to look at each element from first to second last. If the current and the next elements are out of order, you should swap them. And if no 2 elements were swapped in our pass, then we should quit. Okay. In our indexing language, it looks a little bit like this, right? So we're going to repeat this n-1 times, set some variable swaps to keep track of how many swaps we're doing to none, and then for j from 0, so j is going to start at 0 and go to n-2. Yeah, why is it n-2? Well, if we look at our first pass here, this is n-1, right? This is n-2. If I were to go to n-1, then I'd be comparing with some value here that doesn't exist. So we just want to be careful about that indexing. Okay. So if those elements are out of order, we should swap them. And if no swaps are made, then I should quit. Why are we quitting if no swaps were made? Well, if no swaps are made, then we know that we have everything in the right order, and so we can just stop. Okay, so similar to selection sort, our upper bound for bubble sort is n squared. So I need to do as many as n squared steps if my input size is n. So like we saw before, we're going to have n number of passes to make sure that the top value is correct, and then the next one, and then the next one. And then during each pass, we're also going through the whole list to make those swaps. Same way we talked about the linear scaling, this one scales in an exponential way, right? So for every new item that's added, I need to do n more steps, approximately. So for a big list, this gets time-consuming pretty fast. A key difference between bubble sort and selection sort here, though, is the lower bound. So we saw in selection sort, the lower bound was n squared, right? There was no way to like stop it early, but with bubble sort, because we have this checking if we did the right swaps, or if we'd made any swaps, and stopping if we did, the lower bound in this case is going to be n, right? So in the best case, which is if my list is already sorted, I'm going to go through and each pair and see that no swaps have to be made. And then I get to the end of that, it says if no swaps were made, then I just end the program. And so the best case here, we see a lower bound of n. Okay. Finally, we're going to get to merge sort, which kind of takes this idea of recursion that we saw earlier and makes the sorting a little bit more efficient, or at least more efficient than selection and bubble sort. Okay, so let's say we have this same list here. And the technique with bubble sort, or merge sort, is that we're going to be splitting this in half. And we're going to say sort the left half and then sort the right half. Okay, so now that I'm sorting the left half, how do I sort this list? Well, I split it up again. And now I have two lists. I'm going to say, let's sort this left half. How do I sort this list? Well, I split it in half, right? That's kind of the recursive call. And then once I have these two lists of size 1, my base case here, I know that a list of only one thing is already sorted. So that's great. And then we get to the part of merging. So I know that 5 is sorted. I know that 3 is sorted because they're only a list with one thing in it. Okay, and so with sorting it, I'm going to look at these two lists that I have. I know that they're sorted, and I'm just going to compare the first value in both of them. And whichever one's lower, I'm going to put in first. So 3 in this case, 5 after that. Okay, then I'm going to do the same thing with my right half. So I'm going to have 4 and 8. I know that now this is sorted because it's only one thing long, and then 8 is sorted. I'm going to compare these two, which one's smaller, and I'm going to put them in the right order. Okay, so we do this again and again here. Now I have a list of 2 on each side, but I know that both of them are sorted, which is a very crucial piece of information to have, right? So I can look at the first value in each of these lists and compare them. Which one's lower, 3 or 4? I know 3 is lower, so I'm going to put that in my list. Then I'm comparing the next 2 heads of the list, right? So I'm checking 5 and 4. Which one's lower? 5. So then I can say I'm checking between 5 and 8. I know 5 is lower, and then I can put 8 in. Okay, and so we do the same thing on the right side. I break this up, and then I sort 2 and 1. I sort 7 and 6. And then I compare 1 and 6. 1 is lower. Then I'm comparing 2 and 6. I know 2 is lower. And then because that left list is already empty, I know I can just put this list in since it's already sorted. Okay. And then finally, we do the big full list, and we are checking the heads of each of these lists that we know are sorted. So I can say 1 is lower than 3. Let's put that in. Now I'm checking 2 versus 3. Put 2 in. 3 versus 6, well, 3 is lower. 4 versus 6, 4 is lower. 5 versus 6, 5 is lower. 8 versus 6, 6 is lower. Then 7, then 8. And then we have our final sorted list with merge sort. Okay. What if merge sort is already sorted? That's a great question. So that's our lower bound, right? So let's look at the runtime. But first we're going to look at the pseudocode for this. So basically what I just did there was we split the list that we were working with into 2 halves, sorted the left half using merge sort. So that's a recursive call. Sort the right half using merge sort, which is another recursive call. And then merge the 2 halves into a single sorted list, taking the smaller first element from either half. Okay, so our upper bound here is n log n. So I need to do as many as n log n steps to find my solution. So this is logarithmic, right? Like if my list right then was 8, if it grew to 16, I would only need to do 1 more step. If this was like a linear algorithm, it was O of n, then I would need to do, or if it was n squared, I would need to do like 8 more or 16 more steps. Yeah. And then, so if we look at how it scales, it has this like logarithmic curve. Each time I double my input size, the algorithm only needs 1 additional step. Okay. So this is a chart of our runtimes for each algorithm. And that will probably come in handy if you're doing sort after this. And this also addresses the question we had in the chat, what if merge sort is already sorted? That's our omega here. So we can see for merge sort, if the list is already sorted, the runtime is still the same, right? We're still going to do those same steps each time. And so the runtime is also no different. Okay. I'll pause here for any other questions about sorting, runtime of these 3 algorithms. Okay. All right, well, thank you everyone for your participation in the chat. This was CS50 Week 3, algorithms, and I hope to see you next week.